So I'll try to keep it a bit more light, as it is the last talk of the day. And yeah, so HOPS, I will talk about the user-friendly software that I have developed during the last it's been quite a lot, almost 10 years. So HOPS stands for the Holomon photometric software, because Holomon is a mountain here in Greece, where I did my undergrad studies. Here, this picture is taken from the place where the telescopes are. And this is how I started my career as an astronomer with an ATIC 4000 camera, 11,000 camera, a C11 telescope, and an Atlas mount. Back then at the station, we had no software to do the data analysis. So this is where everything started, and this is why it's called Holomon. You can find the software in this link. It's in many other slides later on. Let me close this, okay. It's also in other slides later on, if you want to have a look at the software, download, or read the manual. I will try to give you a brief overview, and mainly why I spent some time to do this. So, no, not working. Okay. So there are some limitations about data analysis for exoplanets, at least for a newcomer. I was a newcomer back then when I started my undergrad, and well, money, of course. we didn't have much money for software that we could pay for. There was, of course, a steep learning curve. You need to spend a lot of time, apart from taking the data, the observations, then usually people were spending a lot of time to analyze their data. Then the processing time is also, even if you knew how to do it, then it would take a long time for each observation to get analyzed. From case to case, it requires some coding skills, depending on your observation, or some software used to require some coding skills. And of course, then the interpretation was a bit difficult with the tools that were existing back then. When I started, I actually was working with amateur astronomers very often, and they actually knew a lot more than me. So I learned a lot from amateur astronomers, and I was interacting with them all the time. And this is where the idea of creating a tool came up, because after I learned how to do it, I thought, okay, maybe it would be better if I try to make it easier for everyone, at least as easy as possible. So this is how the software, the main characteristics of the software is that it is open source code. So it is open to contributions from other developers. If anyone is interested, so the code is open. And most importantly, also includes a graphic user interface and works easily on Linux, Macs or Windows. So there's no need for scientific coding background or anything else. You just interact with it like Windows, and it's as easy as possible. It's written in Python, so it's quite easy to implement new tools. If, for example, as new tools are developed at the moment, Python is the most commonly used language among astronomers and data analysts in astronomy. So it would be easy to implement new stuff, and it's quite flexible in data format. So it should be suitable for most small and medium class telescopes, the ones that usually do not need any dedicated calibrations for the data. Of course, in my everyday life, I work with Hubble Space Telescope. It would not work for Hubble Space Telescope data because they're very specific, but with smaller and medium scale telescopes, that would work very good. So why HOPS? As I said, two main things were the motivation. So inclusiveness in one side. In this way, having a user-friendly software, as I said, with not much knowledge on coding required, where not very steep learning curve, it opens the window to more people to get involved in the data analysis. In this case, about exoplanets, but I believe that these approaches would be very helpful to other scientific fields as well. The more easy the tools that we have, the more easy it will be for new, either students or amateurs or like anyone to get involved. And of course, it's the knowledge transfer between communities. So this recently with astronomy and other packages like the AstroPy collaboration, it has proven to be very efficient as as more codes have been developed are shared easily among the community, so other people don't have to rebuild them. So sharing tools is easier in this way. Then, of course, this gives us a better use of the resources. So as it reduces, or an easy to use software reduces the overall time that we need to spend on data analysis. For example, well, from what users tell me at least, it may take a few minutes to run the code and get your light curve or transit light curve, while in the past, we used to spend a lot more hours on this. The results, of course, are still of high quality. So while the effort is reduced, the quality also stays high because the tools are developed with high standards. So it's just that the parameterizations and the different options are a bit more reduced, but the making something easy doesn't always mean that you make it of lower quality. And of course, science is fun. I mean, I would always like to use a code, even in my everyday life, that it is easy to use and it's fun using it. So this is all why HOPS and why user-friendly and why GUIs and interfaces and all this. But let's see in practice a few of the functionalities that HOPS provides and a few of the problems that sometimes we have when we observe, especially exoplanets. Because in exoplanets, we usually need to observe for a few hours. Well, in the best case, like 3 hours, 4, but it could be up to 7. So you would like to know if your target is visible throughout the night. And one thing is that usually your horizon, for example, is not really uniform. You have some trees or some buildings here and there. So this diagram here shows the horizon that we used to have in the Holloman observatory. And you can see that here is, well, it's the accumulation, but you can imagine this area here, the peak is about the west, where we had some very nice trees going up to more than 50 degrees. So one of functionality that is built in HOPS is an observing planner, where you can include some information about your horizon and the target, let's say here is Andromeda, that you want to observe, when you want to observe it, and it will give you a diagram from day to day at what time the target rises, what time the target sets based on your horizon, like here, what time goes behind the trees, for example. And yes, of course, together with information about when the sun is up, like the yellow stuff here, when we have twilight and when it's dark, and how dark it is based on the moon phase. So here is more like full moon, here is the new moon. So things that otherwise would look very complicated, but you want to have it like in hand quickly when you plan to observe, especially exoplanets, as I said. Now, once you've done your observations and you have collected your data, we need to go through them and process them. So HOPS gives you the usual steps. First of all, it's reduction, creating the master bias, dark and flat frames and applying them to the images. You don't have to do much more than indicating, of course, your frames, which frames are your field of view, which frames are your bias, dark and flat, and then the correction is applied. Then one thing that is also not very common is identifying some frames. So for example, it's very common, especially in long observing runs like we do in exoplanets, to have some clouds coming in or out, or some aeroplanes coming in your field of view. So it has HOPS has a built-in functionality to identify, for you actually to identify but frames here. This is as a diagnostic, it's using the sky background. So when sky background is going very high up, you can imagine that you have a lot of clouds. So you can start picking up and deleting, actually indicating that these files are not very good, and the code will keep them out. You don't have to go through them one by one. Now, after this, here comes the difficult part. So our telescopes, at least those at the Holm station, as I said, they had a very, very, very bad guiding system, so that the field of view was moving a lot. And all the tools that were available back then were not really able to adjust to this movement. So we were ending up throwing many data sets because of this problem of not very stable guiding. And I can imagine that this may be the problem with other smaller systems. So the way that HOPS implements an alignment is by creating a mapping polar coordinates about the stars that are inside the field. So you don't, it's not really plate solving everything, but quickly identifies any movements, even if they're large scale, and even if you have Pierre flips that are quite often. So it gives you in a few minutes, in a few seconds, in some cases, without a lot of trouble, the alignment coordinates, so where the stars are moving throughout the night. And then we go to photometry. So the code will indicate to you where, so here in this case, this red box gives you like the useful field of view. So the area that is always visible. You can see here that there is a lot of drifting in this case, because most of the area here at some point goes outside the field of view. That's why it's indicated as, well, look, be careful, only the stars are continuously in your field of view. And you can select your target, and then the software will give you some indications about which targets are good for comparison stars, because it's doing relative photometry. Yeah, you can go through and select your targets and your aperture size just by clicking on the image here. And after running photometry, so you get your light curves, the raw light curves here on the left-hand side. Yeah, this is the first picture that we always look when we do the exoplanet transits. We're very happy to see that there is a transit, there is a dip. Well, okay, but that's the first look, and it's very good. So HOPS is applying two ways of doing the photometry. One is the aperture photometry, where calculate the flux within a circle around our target. And the second is the PSF, where the code is fitting to the ellipsoidal on your star PSF. Ellipsoidal, not a Gaussian, because when not symmetric PSF, because many times we have elongated stars, as we said, but guiding was the key driving for this software. So would like to some case capture any badly shaped stars, like slightly elongated. So that's why the code is applying a non-symmetric PSF to get the flux of the star. And in the end, I will not show you all the details and all the different parameters that go in here. We can talk about it later in the discussion, but once you have your light curve, the code gets some of the parameters from known catalogs, and well, it gives you the option to run a fitting on your data. This is a Markov chain Monte Carlo fitting. It's well, one of the standard ways astronomers, well, analysts generally try to fit their data. It takes a bit more time. This one, of course, a few minutes, because millions of models are checked. But in the end, the code gives you this nice result with your light curve, where a detrending method is also taken into account. It's very common that during the night you have trends, either because of clouds or because of air mass, which is the most common. So the code tries to find also the trending method to get rid of the systematics. So in the end, you have a flat light curve with your depth fitted and your mid-transit time, which is very useful both for exoclock and orbits, as we talked earlier. So from the plot at the end, you can just get your time, which has been converted to the standard barycentric Julian date, corrected for the leap seconds and everything. So code takes into account that is for you. And also gives you the residuals where you can judge whether the fitting is good or not, and a bunch of other diagnostics that are not shown here, but there's too much detail, I think, in this to show in this presentation. But there are a lot of indications to tell you actually if the fitting is good or bad. Then if you are part of the ExoClock project, you can just take this light curve and upload this to the system. Another fitting is done there just for consistency reasons, because here you can use, of course, the software for any exoplanet observations or any observations, really. You can do the fitting of any exoplanet on your light curve. On ExoClock, there are only the planets that are within the target list for ExoClock. But here you can do the fitting for all of them. And well, working on the updates, we have changed the output to be also compatible with ETT. So observers that use HOPS can have the option of saving the results in a format to be submitted to ETT to help also to actually also help observers who want to upload their data to the ETT database. Now, I have not changed this slide more than 2 years now. There's a lot of work that needs to be done in the future. I see the message. Okay, so there are a lot of things that users have requested and also would like to include, like observatory specific reduction for cases, for example, where non-linearity corrections the observer would like to implement non-linearity correction for the camera, or a Gaia catalog for a better identification of the target, all sky photometry, which is very useful for surveys, especially for variable stars detection that many people, I think also here, are doing. And also eclipsing binaries modeling, again, from the community of variable stars. Unfortunately, I'm the only developer at the moment, so things get a bit slow. But yeah, at some point, we will get there. So I'll just leave you with these basic characteristics again, and I would be happy to answer any questions you may have. But if they are too technical, maybe we can talk during the discussion or even privately if you want. Thank you.